Okay. Can you guys be my recording cops if you notice that I haven't, like, that, if that red button, like, just to remind me so I can, sometimes it starts and stops, and sometimes if you take a break, it'll stop, whatever, so I'll try to put this stuff up. I won't try, I will put it up if you're recording, okay? All right, guys, so the simplest thing is 2 wires, okay? 2-wire transmission line. Okay, so if I look at the cross section of 2 wires, okay, and you'll see why we need 2 wires. So this is cross section. You'll see, like, if the 2 wires are coming towards my face, I just see these 2 sort of gauge things, right? Then we have what's called a coaxial transmission line. So this is like your cable, actual cable, the cable modem going in your house. You've seen this sort of coax. And what it looks like is there's an inner metallic core, okay, and there is like a dielectric around that, and then there's an outer metallic shield, so-called. Okay, so this is the inner conductor, this is the outer conductor. Okay, and you basically, when you're putting in an input, you put the input here, and you ground the outside. And if I look at this from a cross-sectional view, I'll see sort of the inner core and then the sort of the outer shell. Okay, so let's see. So those are like stuff that you see. Then there is the transmission lines that you might see in a printed circuit board. Okay, so the next few I'm going to draw for you is stuff that might show up in a printed circuit board. Okay, so I'm assuming you guys have all seen printed circuit boards, but again, basically, like this thing is. Have you ever seen printed circuit boards? Really interested in looking at this? No, there's nothing magic here. But you see these wires here connecting these components. Okay, and what they are is there's copper metal lines that are patterned, and then there's dielectric in between them to kind of prevent stuff from shorting out. And then the reason you have this sandwich of these things is because you can have lots of interconnections. If you just had one layer, pretty soon, like all this stuff here would block anything would be coming across. Okay, so you put another layer underneath it, so you kind of come across, go underneath. And usually these things have somewhere between 4 and I've had 4 to 10 or 12 layers of interconnections, different costs and different things. They might be able to do much more. Okay, so these, as you guys will see, that digital stuff is fast enough now that even in a board this size, something really small, you have to worry about transmission line effects with these wires. Okay, maybe not this particular one because it's like, I don't even know what this does. It's probably a cheapy board, not doing something too exciting, but certainly in your cell phone. Okay, something that fast, your processor's running at a couple of gigahertz or something there, and you'll see what that means. Okay, so this kind of board, you'll see sort of 3 types of transmission lines there. Okay, each one will have a slightly different equation. So I'm just giving you guys the names of it. Okay, so the first one is called, let me make sure I get all the names here. Okay, so the first one is called microstrip. You guys don't need to remember this for now. If you're really doing this work, or they have tools online. Let's say you're designing a printed circuit board, and you're trying to figure out how to build that transmission line. You sort of, it asks you, is it a microstrip? Is it a strip line? Blah blah blah. Right. So you have to remember it then. It always confuses the hell out of me. So I'm just giving you guys the names, not necessary to remember it at this point, as far as I can maybe down the line. So what does it look like? So there, it's got like this copper wire, okay, is sitting on the dielectric. And then you have a ground line, which is another piece of copper. So this would be, say, the signal. This will be the ground. And cross-sectionally, if I look at the cross-section, it looks like I've got this copper on top. I got this ground, and then I have this dielectric. And this is called a microstrip. Okay, as you guys can imagine, you can only have this on the top and the very bottom, right? Because there's air out here, there's no dielectric out here. So the only place that I have that's like that is the top, that's the two sides of this thing, right? The inner layers, there's dielectric on both sides of my metal, right? So the inner layers will have a different kind of transmission line where you have, essentially it's kind of embedded. So you have, I'm just gonna draw the cross section of this because I'm really bad at drawing. Okay, so imagine you have the copper, and then you have some other, like a ground plane on this side, ground plane on this side, and in between, whoops, there's the dielectric. Okay. So imagine if I had a printed circuit board, what would happen is I would have sort of another layer of dielectric here, and then I'd have another piece of metal up here, and the very top and the very bottom, there'd be microstrip. All this stuff in between, any transmission line you put in between is this thing called a strip line. So that's another name for a transmission line. Okay. And then finally, we have this thing, which is my favorite. It's called a coplanar transmission line. I wish I had a cure for my bad handwriting, guys, but you're just in trouble. You have to deal with it. Sorry. And that one is two metal lines next to each other, okay? And the reason you do the coplanar one is, so notice all these other ones, there is something called, I don't know if you guys are familiar with single-ended or differential signals. So single-ended signals is you have a ground, there's a reference plane, and there is a signal getting launched. So notice there's a ground, ground, signal, ground, signal, okay? So that has some benefits as doing single-ended transmission, but then you can also have a differential transmission. Okay, differential transmission means you have sort of the signal and its sort of inverse, or acting as both the signal and a reference for each other. And that has benefits. I'm not going to get into that. It's my like bread and butter stuff. That's what we have to do. But so for there, you can't have, it's not like you have a ground and a signal. You need sort of two signal lines. Okay, so that's when you use the coplanar transmission lines. Okay. So those are all sort of, again, this is really just two wires, right? This is a coax, like a cable, and the rest of them was kind of what you see on printed circuit boards or semiconductor chips. Okay. All right. Any questions about that, guys? No. Okay. So go ahead.
So this stuff is actually pretty small, right? If you want to fit on like a board, how like small is the distance? Is there a specific distance between each like strip line or microstrip that has to be put so that they won't interfere with each other?
Yeah, yeah. So you have to have a good, so typically on a printed circuit board, you have the, so, let's do printed, PCB stands for printed circuit board, okay. So you're working backwards from what a manufacturer can give you, okay? So the dielectric in a printed circuit board is this material called FR4. That's a dielectric. So it has a certain, like, dielectric constant and certain loss and stuff. I don't remember what they are. Okay, so typically the minimum width of metal you can have a printed circuit board is somewhere between sort of 100 to say 150 micron is the width. Well, let me put it in the same color. Is the width of the metal line. Okay, and then let's say so this is the width of metal line 1. So let's say you want to make a coplanar transmission line, right? So a certain width, you can make it between 100 and 150 microns. And then this sits on a dielectric. It's a certain thickness, and let's say you have opportunity to put a ground line here. Okay, and this distance may be like, I really don't know what the distance might be. It might be another 100 to 200 micron for the thickness of the dielectric. And the minimum separation you can have between two lines may be 100 micron. And this thickness might be, I don't know, 10 to 20 micron. By the way, micron is 1 times 10 to the minus 6 meters. So it's a millionth of a meter, what I'm telling you guys. Okay, so, so the tighter this number is, at the manufacturing place, the more expensive this board. Okay, because it means you can pack more stuff in. So practically what happens is when you're designing your board, usually at the printed circuit makers, they have a lot of them have this sort of like transmission line calculator on their website. So you kind of drop down what kind of transmission line. You have a choice of coplanar, microstrip, or strip line, okay? Then you give it, as we'll see, an important parameter for transmission line is the impedance of the transmission line. We'll see in the next hour or so what that means. It asks you, okay, what would you like the impedance of the transmission line to be? With the typical parameters that you'll see in a printed circuit board, like 100 ohm to 150 ohm, 50 ohm is hard to get. I'd say like maybe 80 ohm to like 150, 200 ohm is reasonable that you might be able to get. And then it'll tell you, okay, I know I'm the manufacturer, so I know how thick this is and how thick this is. So make this 100 microns wide, make this 100 micron wide. It'll tell you that. Typically, they tend to be kind of those type of 100 microns, 200 micron kind of things. That's a very long answer. Is that kind of what you were looking for? So, and then there's the added confusion. If you guys are gonna I'm just telling you this for the future, because this has crushed missions to Mars. I kid you not. So, for whatever reason, Americans have decided that anything inside a silicon chip is in meters. Okay, so again, I'm in the silicon chip business, so we talk about micrometers, nanometers, those kind of things. Anything in the package and the printed circuit domain is given in mils. Mils, a lot of people confuse this is what crushes missions to Mars. When they hear mil, they think it's millimeter. It is not. Mil is 1,000th of an inch. Exactly, my expression exactly. But the first thing you do is you'll think it's millimeter, and that causes every time, because you want thing to ask, millimeter, to sound like something that makes sense, okay? So everything, so I had it in my head, I'd have to translate this in my head about what, so if you go to a printed circuit board manufacturer and they're fancy, they'll go, oh, my minimum width is 4 mils. So a mil is 1,000th of an inch, which is 25.4 micrometers. So 4 mils is about 100 microns. And that's what I wrote here. But you'll see it in mils. They'll say, oh, it's a 6 mil line. And they'll say, oh, this is 4 mil thickness.